Uh, Yesterday we saw a lot about VIP thanks to Fabrizio's talk. And so now we are going a little bit in detail. So far we have talked about theories. Now we go a little bit about some analysis, so a little more practical. So just to remind about some jargon, but I'm pretty sure everybody is already aware of it. VIP is looking for X-rays. X-rays are given through the cascade when an electron is captured in one of the one of M or L shell, and then they cascade to the K shell, and they produce X-rays. Typically, well, the classic nomenclature, when you have an electron captured by the L shell and goes to the K shell, it's called K alpha, while it's captured from the M shell, it's called and the K, and cascaded to the K shell is called K beta. In our case, we will focus on you will see soon, we will focus on the K alpha. Also, another things, one more thing that Fabrizio said, it show you about the shielding. So you have already one electron, 0 or 1 electron in the K shell, you have K alpha 1 or K alpha 2. So because the presence of electron is shielding, and therefore you have a little less of energy when the cascade occurs. If, and that's the point of it, if there were already 2 electrons inside a K shell, you will have an even smaller energy in case of a cascade. But this is a situation forbidden by the Pauli exclusion principle. However, the Pauli exclusion principle is connected to the question why we have a Fermi-Dirac and a Bose-Einstein statistics, because we have the anti-symmetric and symmetric commutativity. In case we break it, of course, we will have Pauli exclusion principle violation. Why this should occur? We have some theories. Fabrizio did a very splendid job yesterday to explain it, but just to summarize, we have the Green's general quantum field, which he made the hypothesis that the fermionic bosonic field is just one layer of the fields, and then we have, it's called, but in the jargon, order 1. And then we have also different layers of superposition wave function. In this case, we have of higher orders, and in this case, we have the parafermionic or parabosonic fields. And plus, we have from Messiah Greenberg, we have, he proved that there is a kind of super selection. Since they are the same particle, there is no fermion that can become a parafermion, and no boson can become a paraboson, and vice versa. So either you have an electron that is already respect the fermion statistic, or either is respect the parafermion statistic. They cannot mix because they are the same particle. And that's why the particle, they were defined with this fancy name called paronic. So a paronic particle, for example, a paronic electron, is the superposition of a fermionic wave function and a parafermionic wave function. And of course, is one of the 2 when they collapse. Another possibility to break the commutativity is when you have the non-commutative quantum gravity. For example, theta Poincare. In theta Poincare, you have a distortion of the Lorentz symmetry. A lot of people have discussed about it, so I'm not going further. And in all these possibilities, we have the chance to have a PEP violation. And of course, from the experimental perspective, if you find a violation of the Pauli exclusion principle, you have some kind of limit, or at least something to say about these possible theories. In our case, in case of VIP, since we are going to talk about it, we have the chance that a third electron decay and goes in the K shell. Sorry, decay, it does cascade and goes in the K shell, therefore violates the PEP violation. The PEP has a probability called beta square half. This is also were introduced by Fabrizio. And this is basically the measure we would like to have to test all these theories. VIP, you see here in the pictures. So here you have our detector is this guy. This is the drawing, it's a box with a vacuum inside. The target is a copper strip. You made flow current inside of it. You have STDs surrounding and keep surrounded the target, and they are kept to a stable temperature, minus 170 degrees. And of course, since you don't want disturbance by cosmic rays, you place in, for example, in underground facilities, in the Gran Sasso in our case, where you have a rock shielding and of course shielding from muons and cosmic rays in general. So the experiment works we detect two cases. The case with current in this pink orangish color, and sorry, without current. So this is basically the control measurement, whatever you have from nature. And then when you let it flow, when switch on the current, 180 ampere in our case, you take again the data. And as Fabrizio said, since when the current flow is injected, you are injecting new fresh electron, and these new fresh electrons, they are those, if one of them is parafermionic, is gonna violate the BP in case is capture and do cascade. So here we have the spectrum. This was also shown yesterday by Fabrizio. However, Fabrizio shows 6 months of data taking. Here I'm showing you 2 years of data taking. I'm not showing any numbers because it's going to be published, but these are just a preview of what you will see in our next paper. And in this, here you can clearly see the two colors, the blue with the current and the pink orangish. This depends on how sensible is the monitor, is without current. Basically, the two spectra are quite similar. This peak is the K alpha from the copper, which from the target, which is the one we like. And this is, for example, nickel, because you have some background. So this, and plus, of course, you have
something here. How would the signal look like?
I'll show you.
Oh,
okay. I'm going to show you. So, and of course, we have here some background. So, in case of without current, we can make a model of this, of this spectrum made with some Gaussians, because they're describing the two peaks, nickel and copper, and plus, of course, as we say, the background here. The parameters θ1 and θ3 are the centroid, θ2, θ4 are the enlargement due by the detectors, and of course, then here you have polynomial, and the y's are the amplitude of the different peaks. In case of, and that's your, I'm going to answer your question. In case of the presence of a PP, we know by calculations that the peak is centered at this energy, 7,729 electron volt, and of course it should be another Gaussian. The sigma of this Gaussian, for obvious reason, because it's the same detector, is the same of the copper. That is very easy to describe it. And in fact, in the model of our spectrum in this case is identical of before, plus we have a further terms. In the further terms, there is only θ4 because is the sigma of the peak of the Gaussian. And plus we have the amplitude S. We didn't call Y, but S, because it's exactly what we want to measure. We want to set the limit of this. So once we have our model, we can clearly create a likelihood function. The likelihood function is trivially the product of the two Poissonians. Two Poissonians in case of without current, with current, and without current distribution, where D are actually the data, so what you are looking here, and of course F is the model that I have described so far. Another one thing, since the two distribution, the two spectra, they should be exactly identical except for the presence of the PP here. We want also the same thetas and the same y's. But since the data taking is slightly different, of course, you need to multiply, in this case, the y's with a ratio R, which is the ratio of the two data sets to normalize the two spectra. Now that we have our likelihood, we go for the analysis. Fabrizio say that we have done two methods, one Bayesian and one frequentist, and that's true. The Bayesian, of course, is the most basic one because it's well established, well tested. We know everything about the Bayesian when we have few counts, so we can rely on that. And here we have our posterior. Is built like this with a likelihood, with P's are the priors. And since all parameters are independent, the P is just the product of single priors. And the priors, they are built through the knowledge we have from previous experiments. In case of the thetas and the y's, since we have previous measurements, previous experiments, we know basically the central values, and you can describe as a Gaussian because statistical fluctuation. While S, our parameter, what we want to know, to not be biased, it must be treated like a flat distribution, except is limited from limited by 0 because you don't have -1 signal, of course. And the upper limit of my flat distribution is, of course, given by previous experiment because we know that at some point we don't know anything else. We don't have anything for sure. So we have our Bayesian. Once we calculated, we can we marginalize our posterior. So we integrate with all the parameters we don't want it. And in the end, we have a nice distribution for our posterior of S. And it behaves like a decay, as we can see. So we have, of course, we can calculate the area and having the 66, 90, and 95% of coverage or confidence level. So from this plot, it's quite easy to see how much is my S. For example, with a 90% of confidence level is approximately 80, like this. That's my count of S. Going with frequentist method, actually, we don't use a pure frequentist, but what is called a modified frequentist, and the method is called CLS. What you do is working through a test statistic. Actually, it's a one-sided test statistic. For simplicity, I didn't place that TS is equal to 0 if my S is negative, because obviously it's obvious. And so we can build this function. So we have here a profile likelihood like this. The profile likelihood is the ratio of these likelihoods. And now I'm going to explain what they are. To note that compared to what we saw before is written slightly different because this includes the likelihood I showed you before, plus also the prior we discussed earlier. But in this case, priors are not priors because it's a frequentist approach, as not Bayesian inference. These priors behave like penalties because, of course, my parameters, I expect to have certain values. And then I have a Gaussian distribution and also S at some point. I don't have more values of S. So that's basically behave like penalties. So what kind of likelihoods are? The denominator is the classic likelihoods. So you have function, you try to find what are the parameters that the best fit your likelihood, the maximize your likelihood. And Then you have your expected values, theta hats, y hats, and s hat. The nominator, the numerator, sorry, actually is slightly different because it's more tricky. What we do here is not let S to be free to maximize my likelihood, but I'm giving fixing values one by one. So I'm testing how much is my S. How much is for example, if I place here S equals 0, truth is likelihood I will obtain my theta hat and Y is hats. And of course, I will obtain a certain value of my t. Then I test is s equal 1, then is s equal 2, etc., etc. In this way, this test is estimating the deviation for each given possible s I'm testing from the expected, because the denominator is the expected. And now comes what is the CLS itself. If I take in consideration all the possible TS, so I have a distribution of these TS, and I can calculate my p-value, the p-value as we know about it, integrating from the t with the f's observed, the f that I am observing, up to the infinite, so up to the whatever s I want. But, and that's a big but, the p-value is not exactly trustworthy. And that's why through this test, I'm creating this small function, this p-value, which is testing how much the p-value I calculated is deviating from a normalization. The normalization is 1 minus p0. P0 is when s is 0, so it's the background case when my s is 0. And this is, and my CLS should be smaller than 1 minus confidence level. In our case, we want 90% of confidence level, must be smaller or 0.1. So in this case, we can do a computation and present this plot. Also, this plot was shown by Fabrizio yesterday. Still, I have, he showed 6 months, I'm showing 2 years, and I'm going to explain a little bit more in details what is this plot, because this plot is hidden inside two important information. The first one, what are you looking? The color regions, this one, are the expected distribution of my CLs in background hypothesis case. So this is my null hypothesis. How it looks like. How it looks like given if my true S is a 0, but I measure an S of, for example, 150, how much is my CLS? Here in the green area, you have the 1 sigma of deviation. In the dashed is the expected median value of I get, then the area of 1 sigma and 2 sigma is in yellow. And this is my null hypothesis, basically. To be noted that the null hypothesis is computed creating, so the system creates a fake data set called Asimov data set, because it is the most ideal data set to maximize as the most possible the likelihood. So it's the most ideal data set you can have. And that's how is estimated the background case by the computation. So in case of my real S is 0, but I measure something. And of course, in this plot, you see the dots and the solid line. This is actually what you observed from the experiment, so the real data. Here you have, and of course, here the red line is my 90% of confidence level. So with my p-value, my CL, so 0.1. Okay, what information gives you this plot? Give you two information. The first, as the previous one, you can estimate exactly what is your upper limit. Here is confirmed to be something like 80. Sorry, there is, okay. Here is confirmed to be something 80 again. So we confirm what the Bayesian analysis gave us. The second is how much is reliable compared to the null hypothesis. In our case, it's still compatible with the null hypothesis inside 2 sigmas. So that's the important feature of this plot. Okay, so now that we have our measurement S, how can we go from S to beta square alpha, which is the probability of interaction we want, the probability to have the PP violation? Basically, it's a simple formula. We have the number of counts you expect is given by this formula. Now I explain step by step. This one NX is exactly the S I have measured. Beta square alpha is of course the probability, and nu is the number of new electrons I'm injecting inside my target, because yesterday Fabrizio explained that in a closed system, so if I keep the electrons as they are, if there was already a PP violation, already is done, so you don't have any information. But if you inject new electrons, then these electrons are tested inside all my interaction point. In fact, then of course you need to multiply by the number of interaction points you might have, divided by 10, because we know that every interaction point approximately, every 10 interaction point approximately, 1 is captured exactly to make our cascade, the cascade we want, the K alpha, well, K alpha 2 in this case. And finally, the number there is, of course, the efficiency of VIP. The specific efficiency of VIP is counting the X-ray set absorption of the target, the geometric acceptance, and the SDD's efficiency, obviously. So trivially, if you invert the formula, you have, so this is quite banal. However, in this formula, you see that there is something extremely important, which is my number of interaction. Number of interaction is something that you cannot know, you cannot measure. Therefore, you need some models. And actually, number of interaction works as a normalization parameters. Basically, is thanks to this number that you have the real scale of your beta square alpha. To be noted that if you want to improve the experiment, of course, improving this, the current, the time, also change how is S. So it's at some point you reach some kind of plateau, experimental plateau. So it's not probably to have one order of magnitude better, you need 10 years of data taking, which is quite impractical. You can also improve, of course, this part, which is your efficiency. However, the real the important part that gives you the scale of our beta square alpha is the number of interactions. Okay, so let's try to discuss a little bit a couple of models we have. The most stupid one is the linear scattering. So copper has a resistance, so you know that there is an average interaction length, mu. So every mu, you have on average 1 interaction point, like this, because you have the sides, you have the length, simple. However, this is a super naive model, because this kind of interaction, they happens because phonons and lattice irregularities, which is not exactly the interaction point that you want, is extremely underestimated in this case, because the electron is interaction point of this electron that is coming inside my my target is every atom that encounter. So in this case, I testing only when encounter some irregularities. Therefore, this is a super underestimated. However, is the most robust for sure measurement we have. And the scale goes to beta square alpha around 10 to minus 31. The next model, the one that we tried actually to see, to estimate our electron passing through and testing encountering every atoms, is a little bit more realistic. It's a bit more accurate. However, it's still a simple model we have done, so we try to improve also the model to have a more solid one. But in this model, you simply we are using the diffusion transport theory. So you have here the reservoir of electrons that is going to be diffused here. When you activate the current, actually you're improving this diffusion. So you can estimate through the theory and knowing the density, the atomic density of the copper, how much time passed for an electron encountering one atom to the next atom, to the next atom, etc. Then you know, of course, how long you need to take for the electron passing through the copper. And then we have your interaction. Still, as a simple semi-classic model, one dimension, using a diffusion theory. And in this case, actually, we have a huge breakthrough because the number of interaction is 12 order of magnitude higher. So in fact, the beta square half is around 10 to minus 43. And so having that's what I say before, having a realistic number of int estimation is basically changing the scale of your measurement greatly, really greatly. Okay, so yeah, of course, there is also some idea to try a more quantistic approach, so testing the field of the electron, how is the probability to encounter the field of every atoms, but this might be a huge work and we need time also to think how to do it. However, so this concludes some conclusions. We have these two approaches. The Bayesian one is established, and we need to take care about the systematic carefully, but is basically the main analysis you can do in these cases. We have also the CLS as a cross-check, because Bayesian analysis, since the Bayesian inference rely on priors, so there still might something unknown that causes some mistakes. So it's better to have a second check to a second kind of analysis to check that everything is in order. So at least we have the same values. And CLS give us a little less, is a little less sensitive of Bayesian. In fact, we more or less they give the same result, but CLS is slightly worse. You must trust about that because I didn't show any number and I won't. But basically, the advantage of CLS is a method that try to check the minimum changes outside the null hypothesis. So in this way is try to minimize the fluctuations you have with a more classic frequentist analysis. And that's a very good advantage because small changes of the parameters imply that you can actually see in the test, while in a classic frequentist might not be so clear. And of course, the main important issue that we are trying to improve to have a very solid measurement is the estimation of the number of interactions. That we have, I show you two models, a linear scattering, which is the safest hypothesis, but also is largely underestimation because, well, you are checking one interaction point every and that actually happened. And then we have, of course, the close encounters that is more realistic and it has a very huge improvement. But we are trying to improve this model to give more robustness to this hypothesis. So thank you.